Hi guys. Actually, I already received the machine data you sent me. So we have now all the your machines, Donovan machines, on the cloud. So if you edit any machine, you'll see the details: manufacturer, model, serial number, CNC, and obviously the facility. So what I would suggest is to run a Ballbar test in 360, and let me show you how to configure that. So we are in a setup and run. And here I'm gonna select each of these machine one at a time, and we're gonna hit next. And here we can create a new test. So once you create a test file or test configuration, you just need to reuse that. You don't need to create a new one. So in that way, all the tests you do are going to be uh, based on the same parameters or configuration. So usually what we do, even in those CNCS lantern uh, bed, um, what we use is this configuration: horizontal lathe. Uh, And the feed rate that we suggest now is to use 3000, but you need to make sure if your servo motors, uh, let's say if your servo motors are 3000, sorry, 3000, 30,000. Okay, yes, 30,000. So let's say if your servo motor are the maximum RPMs are 3000 RPMs, and you have a ball screw 10 millimeters pitch, 10 by 3000 is 30,000 millimeter per minute. That is what you need to know. So here we use the most common is only the sensor without any extension. You can in small machine you can run 50, but I don't think this is your case. So at least you can run 100 millimeters. The sensor is only the sensor length, and making a circle. So here you can add the program name you use. Let's say, for example, 0999 or 911 or wherever. And here, what we just suggest is to use an incremental part program. So that means in any place you position the axis, that is going to be the zero position. And then from there, you are going to run the circle or the Ballbar test in incremental movements. So let's say to define the zero, usually we use G54 and parameterize X, let's say 351, C, uh, 46, 456. So this coordinates is going to be our zero position or zero reference position for the circle that we are going to describe with the ball bar. So these are only details, notes. They won't affect the measurement. You can define how many spindles you have, and we set up the calibrator just to every time that we run the Apple bar test. Previously, to do the ball bar test, we set the sensor on the calibrator and make sure that it's um, calibrated all the time. And let's go here. Here you will see where is going to be the zero on the circle. And then let's say we used to start all of them in C plus. Let's say if this is your configuration, or probably you have two turrets. Let's say if we're in the upper turret, you can rename the axis. And let's say we have XA and C8. Okay. And if you have lower turret, what you can do is to swap the position on the axis. Usually the spindle is here at the left or the headstock. And then you have far from the headstock in Z is positive, and far from the center line from the headstock is X positive. So and here we have to change the name. So the other option you have is to start change the position, starting position. So we usually have the axis in any position, move the axis to 0, and then moves only in Z to start running the circle either clockwise or counterclockwise. So let me show you how to do that. So we're gonna run 360, 2 turns, and sorry, let's keep it there. And I can start here, and you'll see this is running in plus C clockwise, the first turn. If you need to change the runnings, you can, if you want to do it clockwise, counterclockwise, you can do it using G02, the second option. But make sure that your part program runs exactly like you see here. So let's rename this, and you can also, if you have the orientation different, usually I think that it's not going to be the case, but you have this option too. And let's say XA and ZA. So try to run a complete circle twice, and at the 30,000 millimeter per minute. Sorry, 3,000. And let's hit it next. We need to, sorry, I haven't saved it. Let me go back and do it again. I forgot to save it. $3,000. Calibrator. XC CX 100. I'm gonna skip this and let me change position there. Okay, so this is gonna be it's gonna save it in your machine, calibrated. Let me show you what we do usually in the on other machines. I'm gonna take any. What was the last one? This was not this. So you see, we have this this description. So let me go back. It's gonna be a X 100 millimeters calibrated, and we are gonna add the comment starts starts clockwise. This in plus C plus or plus C, I guess. Let me check how you see it. Okay, plus Z. And the feed rate is 3000 millimeters per minute. Okay, so let's go back with this description and save it right here. And then you can review the G code. Oh, it's asking me the part program ID. In Cinemag you don't need to put numbers, so let's call it Ballbar. Ballbar 360 30,000 3,000 millimeter per minute. Okay. Oh, it's asking me to completely. I cannot leave it spaces. Check. Oh no, there any. Let's leave it there like that. Okay. And this is gonna be your controller. You can select the controller here. Let's say numeric A40 metric A40D, and let's run the test, virtual test, and then you can exclude the warning text, or you can create a complete part program right here. And this is gonna be your part program. Let me save it. I'm gonna add a new folder. Save it. Let me check how I call that folder on the other machines, just to keep it on a standard. Ballbar test programs. Okay. Um, you don't need. Okay, you can use parameters to change the feed rate, but I suggest to do it at 3000. And Ballbar test program. So this is gonna be your part program. You can move or copy to your machine. So it's gonna be this extension. Probably to not confuse, I'm gonna change the extension to txt, and then you have to rename the extension in Siemens is MPF, I think. Yes. Okay, and then let's cancel here. I forgot to mention that you can remove, or let me show you what will happen if you remove the warning text. What it's going to remove is all these parts, and it's going to leave the comments on the program blocks. And let me create it, and you see you have the Walmart program we set up. You don't need this in Siemens, and the part program you need to run. And let me make sure. Okay, it's incremental. So again, you just need to move to the axis to the start point, and then uh, there you need to set up the Ballbar supports the center, and then you can run the program. Let me go back here. I'm not gonna save it because I just made that modification, the comments. So once you have all configured, you have to go ahead and select the test you want to run and hit next. And let's say uh, make sure that you remove the backlash compensations in all axes. Or in zero. This is important to do the test because we want to capture the real backlash on the axis, and you can set any other comments here. You don't need to modify the file. This file, we want to keep this file as it is forever. So let me click next, and here you need to connect the sensor, and you will have the option to calibrate. There is a button here, and that's what you need to do. Okay, that is regarding the configuration, and let me go back and review the results on your machines. So here we have the first machine, and the circularity must be under 50 microns. So we are out of tolerance here. And you have the top five reversal spikes. Here you will see a help on what is this and what are the causes and the effects and the action you can take. This is going to be in the document that I shared with you, the link with all the details that we added. The squareness is we consider 60, or actually 30 is the manufacturer standard, and you will see all the tolerances. As I said before, all the tolerances or uh, values or maximum values we accept on the document that I share. So uh, let's say if you want to try to modify something and see the effects, you have the simulator. This is not exact, but it's going to give you an idea of what is going on. So let me say I want to correct this error, and you'll see the circularity is under tolerance. So just by fixing one error, or let's say the reversal spike, let's reset this. Um, Play errors, lateral play, dynamic error. Here. Let's say if I correct this, it's not going to affect too much. You see? So that is not a problem, but probably this is due to the compensation. If you have the compensation on the axis and it's overcompensated, it's going to cause that spike. Um, and then play error, we have backlash. So no, we just need to tackle the scaling mismatch, which is the one that affects the most. Okay, and let's go to the other machine, machine number 2. You can access already to this online. Let's see the results. And this is much worse in terms of circularity, and we have backlash. Backlash we consider 50 microns and above to take any action or decision. But you can also play here. The squareness is off. Probably if you have gives or you can adjust or check that. Let's check that. Squareness. You see the circularity is changing here. Let's correct the scaling mismatch. This scaling mismatch it means that one axis is moving more than the other for the same command. Let's say if you ask to describe a circle, it's gonna should be 100 millimeters, and each axis should travel the same distance. But for any reason, these are the scaling mismatch is meaning that one of them or both are not complying with the command that Synsys gives. So let's go back. So this machine need to be addressed. The other one, probably you can start working on something preventive or corrective. Let's check this one. I'm gonna add this to the history, and we have a little bit like the first one, a little bit off, but we have the backlash in Z is too much. But I'm not sure if you have or took this Ballbar without compensation. Make sure that you don't have any. If you did with compensation, backlash compensation, just you need to run another Ballbar test. And let's go back. And let's check the other machine. This is not too bad. Probably you don't need, but if you run it at 3000, you are gonna expose more errors. So that's why I suggest to run at that speed, not fit rate. And try to run the ball bars and the on the wear area where the machine works the most. This is not too bad. Score noise okay. So you can see all the errors. Another comment: you can see all the errors right in the tab table. You have 13 errors that can be captured here. We don't see all of them because they are too small, but you should have at least 13 errors in the ranking. That's what we get the most. So let me go back. So probably here servo mismatch. I could leave this and monitor probably in 3 months as it is. Make sure lubrication is okay. So let's go back and check the last one. I think the last one, yes. On this machine, you have this is 3 times the tolerance, so you have to take care of this one. And you have backlash issues in the Z, squareness. So let me check if we correct the backlash. It's a play error. Let's say we set this and a small value here. We reduce pretty much, but it's not enough. So let's say we correct the squareness, and you see, by playing with this error, you can see what it affects or corrects. So let's say we put this all in 0. This is not real, but you see. Okay, so for now that is all. I would like to see if you can run a 360 Ballbar test at 3000 and share the files, or use this platform to see the results online, and we can discuss there later. Okay. Okay, this is the document online about interpreting the test plots, and you'll see here that we have a description, what is a machine error and test error. Test error are obviously machine errors denotes any machine parameter deviation, and the test error is something related to the ball bar itself. You have to review the mounting, if there is anything loose or something like that. So let's see. We have in parentheses, we have the note that is pointing if it's a machine error or a test error. So in this case, as I said, the tolerance for us is 50 microns, 2000 of an inch, and you have the plot shape, and then you have the causes, the defects, and the correction actions that you could analyze and put it in place. So we have positive backlash is you see we have negative and positive. It's more like the same. Then we have backlash unequal. This is something that usually is related to thrust variance issues or the whole assembly moving abnormally. So you have all the root causes here, possible root causes, and the action you may would like to analyze or explore. And the cyclic error, uh, 2.5 is microns, is the tolerance. So here we have some examples, real examples. We took this here, September 24th. So you have the corrective actions, root causes. Here the ball screw is off center, is damaged. The motor was servo motor is mounting is defect. Coupler or coupling damage. So ladder play and etc. You can review all of these errors, machine errors, and take decisions according to the proposed actions that you have here. And if you need any other advice, just let us know. Okay. Thank you.